Hey guys, so in the past weeks, we have been discussing some applications of definite integrals, namely area under a curve, where we are given the graph of a function y equals f of x, and then we consider the region under this curve over the x-axis between the vertical lines x equals a and x equals b. So we considered this region and the goal was to find the area of this region. And then we also considered area between two curves. So in this case, we are given two functions, y equals f of x and say y equals g of x. And then we considered the region bounded by these functions over the interval ab. So if this is our A, this is our B, and we are studying this region, particularly we wanted to find the area. And then just recently, we also talk about arc length of a given curve. So suppose we are given this y equals f of x over the interval, say, AB, and then our goal was to find the length of this curve. So all of these three scenarios, we use definite integral on how to find their respective properties. So for today, we will consider another application, and this time we'll be having volumes. So you might be wondering how we can find volumes when we are only doing two-dimensional spaces. So a little bit later, we will be considering solids that are generated by plane regions. So let us start. Let us first define what we call right cylinders. A right cylinder is a solid generated when a plane region is translated along a line or axis that is perpendicular to the region. So in these figures, we consider this square here. So this will be a plane region and it is translated this way or that way. So the plane region here is somewhat vertical and the translation is horizontal. Similarly, here we got a circle and this is translated horizontally because the circle is vertical. Same is true with this one and this one. Of course, you can have your plane region to be horizontal, say like this, and then this is translated vertical. So if we translate this vertically, then we will still get what we call a right cylinder. Okay, so take note that when you translate the plane region, all the points all the points in that region are also translated. So if you collect all the translations of all the points of those or of all the points inside the plane region, then you will create a solid. If you look at this, I'm not sure if you can see it, but this one, we have this circle and there is another circle here. So what we actually have in here, particularly the region, is the region between those two circles. So there is a hole in the middle. So if we translate this, it's like we are producing a tube. Okay? So there's this one and then this one here, and then there's a hollow in the middle. Okay? So this is our right cylinder. Of course, this axis here, um, that's that is the one perpendicular to our um, plane region, the plane of the plane region. Okay, The amount of translation, the amount of translation will be called height. So it doesn't matter if the plane region is vertical or horizontal, but the amount of translation, so from this point, say the plane region started at this point and ended at this point, then this length here will be called the height of the right cylinder. Now, if we know the area of our plane region, if we have this plane region here that looks like a Pac-Man, if we know the area of this plane region, then we can find the volume of our right cylinder by multiplying the area of our plane region times the amount of translation, which is called the height. So if we consider, for example, let us go back to this one. This part here, it looks like a square. So if the square has length S, then the area of that plane region will be S squared. And if this is translated, this square here is translated by units, then the volume of this one is S squared H. And this is our usual formula for our rectangular prism, square prism for this case. We have this circle here, and if this circle here is of radius r, then the area of that one is pi r squared. If the amount of translation is h, then the volume will be pi r squared h. And this is the volume of a circular cylinder. So the formula that we are going to use here is actually consistent with the formulas that we know already. Okay? So the question is, how do we find the volume um, of a cylinder if if at every point of translation the plane region changes size? What I mean is, suppose we have this particular solid here. Suppose we know that at a particular slab, we call that a slab or a piece, we know its area. Say area x sub I star. At that particular point, say this is our x sub I star here, the area will be A of x sub I star, and we have the length of this subinterval. The length of this subinterval will be delta xi. So for this particular slab, if we now look at this one, at this particular slab, we have delta x sub k, it's using x sub k, and the area of that cross-section is A of x sub k star, then the volume of this particular slab will be equal to, say, V sub I equals A of, or V sub k, A of x sub k star delta x sub k. Okay? And we can do this to all the pieces of that solid. So imagine you have a loaf of bread and you pass the loaf of bread to a cutter. Then you will have some sliced bread. So one way to find the volume of your loaf of bread is to find the volume of each slice. And then, once you have the volume of each slice, you sum up all those volumes, and you will have an approximate volume of the whole loaf of bread. So same concept in this one. So let us formally state the volume problem. Let S be a solid that extends along the x-axis and is bounded on the left and the right, respectively, by the planes that are perpendicular to the x-axis at x equals a and x equals b. So this is x equals b, this is x equals a. Find the volume of the solid, assuming that its cross-sectional area is a function a of x, is known at each x in the interval ab. So, in order to do this, we use the method of definite integrals. We divide the interval ab into n subintervals, not necessarily of equal length, but if it's of equal length, then it's completely fine. The length of the subinterval, we can label it as delta x sub k or delta x sub I. And since we are given a function, the area function, then we pick one slice. The volume will be given by a of x sub k star delta x sub k. Okay? So here is it. Fix n, divide the interval into n subintervals. Here we say of equal length for easy computation. We label the length to be delta x since it's just of equal length. For the kth subinterval, we choose a sample point x sub k star. The volume of the kth slab, so this particular slab here, is approximated by the right cylinder with width delta x and cross-sectional area A of x sub k star. So if we add the volumes, then the volume of the solid will be approximately equal to the Riemann sum. And if we let n approach infinity, the volume is equal to the limit. As n approaches infinity of the Riemann sum, and if this limit exists, this is just your definite integral. So let S be a solid bounded by two parallel planes perpendicular to the x-axis at x equals a and x equals b. If for each x inside the interval AB, the cross-sectional area of S perpendicular to the x-axis is a of x, then the volume of the solid is equal to this limit of Riemann sum, which is just the definite integral from a to b of f of x dx, provided that our area function is integrable on AB. So similarly, if we are on the y-axis, then, or if we are using the y as a variable of integration, then we have the corresponding formula. So this time, the solid is bounded by two parallel planes perpendicular to the y-axis at y equals c and y equals d. And then same concept. Okay? So essentially, you just need to know your area function of the cross-section. The dy here represents the thickness of your slabs. Of course, the CD, or in the other one here, AB, those are the endpoints of your solid. So, derive a formula for the volume of a pyramid with square base of side length S and altitude h. If we look at the three-dimensional thing, then it could be something like this. Then we have this one here. This is on the side. and then here, and then maybe somewhere right here. That's the back part. Okay, and it said that this is a square base, so this is S, and then the height of this pyramid is H. So this is our solid. But how are we going to represent this um, in a two-dimensional system? So what we can do is to look at one of one of the faces directly. So for example, if we put this in the Cartesian plane and we are looking at, say, this face here, then what we see in front will be a triangle that looks something like this. Here, the height, of course, will be equal to h. Since we are looking at the face, this one here is s. So this one here will be s. Meaning, this point here has coordinates s over 2, comma, 0. This point here, since that's the top of our pyramid, it will have coordinates 0, comma, h. So what we can do in order to find the volume of the solid is we pick a slab. Say this particular slab here, correct? So we will have this slab here. So we pick this slab and find the volume of that and do that all throughout the interval. We know that this slab here has cross-section square. Okay? But the question is, how long is this cross section? How long is this cross section? We can identify the length of that cross section if we know this particular point. This particular point up to this point can be identified. And since, look at this, by symmetry, this up to this has the same length as this up to this. So we just need to identify this particular point. It can be obtained by knowing the equation of the line segment of this side of the triangle. But notice, you got point 0, comma h, and you have the point s over 2, comma 0. So we can easily find the equation of this line. The equation of the line, so we have this. The equation of the line can be written as, so y minus y coordinate, let us choose this one here, y minus y coordinate equals the slope of this line, and the slope of this line is just the change in y coordinate over change of x coordinates of these 2 points, because these 2 points are on the line segment. So we will have here, change in y coordinates, we have 0 minus h divided by, so 0 minus h, y coordinate 0 minus h, divided by s over 2 minus 0. That's the change in x coordinate, s over 2, comma, minus 0. times x minus s over 2. Because I use this y coordinate for this part, I have to use the x coordinate, the corresponding x coordinate. So if we simplify this, we'll just have y equals 0 minus h, that's just negative h. And here in the denominator, we have s over 2. So we can write this as negative 2h over s times x minus s over 2. The equation of this line segment is given by this formula, which means at every point here, you are given the y coordinate, the x coordinate, you are given the x coordinate, the y coordinate of that point will be this one here. So we will put that y, this value here in this part. That will be our y coordinate. Okay? Now, notice that our slab is horizontal. Our slab is horizontal. And this slab moves from the bottom of the pyramid going to the top of the pyramid. So it is the y that is changing every time we move the slab. So what we must do is to write x in terms of y, because the slab is horizontal. In that case, let us just rewrite this. We will have from this equation, we will have s over 2h negative s over 2hy equals x minus s over 2, or that our x will be equal to negative s over 2hy plus s over 2, which means that the point here, instead of writing it as x comma the y value, we will write it as y in the y coordinate. So this one here can also be written as y in the y coordinate, and this expression here will be on the x coordinate. So for every point y, say this is the y, that is your x value. If this was your y, then you can just put here. So notice, if y is equal to h, we expect that the x coordinate will be 0. So if we replace that with y equals h, notice that x is equal to negative s over 2h times h plus s over 2. So the h here will cancel the h here, and you will have s over 2 negative plus s over 2, which is equal to 0. And definitely, if y is equal to 0, this will disappear. Your x will be equal to s over 2. At different points for a given y, then the x value will be given by this formula. But anyway, the x value here is just from 0 to this point. So we need the whole segment, which means that the side at a particular y, the square slab has side length 2 times this expression. So that will be 2x, which is equal to negative s over hy plus s. Which means the area of that slab, the cross-sectional area of the slab is, well, the square of 2x. So that will be equal to negative s over hy plus s square. Okay? Let's write it. So a of y, take note of that, a of y will be equal to negative s over hy plus s squared. So if we do the computation, we will have here s squared h squared y squared minus twice the product 2s squared over h y plus s squared. Therefore, the volume of that pyramid will be equal to the integral. The lowest value of y is 0. The highest value of y is h. So the integral will be from 0 to h of this a of y dy. But we already know a of y, so this will just be the integral from 0 to h of s squared h squared y squared minus 2s squared over h y plus s squared dy. Integrating, we will have s squared h squared y cubed over 3 minus 2s squared h y squared over 2 plus s squared y evaluated from 0 to h. From 0 to h, when y is equal to h, this will be h cubed divided by h squared. So this will be s squared h over 3. Here you will cancel this one and this one. When y is equal to h, y squared is h squared over h. So you will have minus s squared h plus, of course, for this one, we have s squared h. And then when y equals 0, everything will be 0 in here. And notice this will be equal to s squared h over 3. And this is the familiar formula for our pyramid. Area of the base times height over 3. Our base is S squared, or S, side length S, take note, that's the base, and the height is H. Right? So that's how we do this. Now, for this topic and in the next topic, our focus is a particular solid. So I would like to skip this particular example, but you can work on them. Try to imagine how the solid looks like. But our focus is this particular solid. We call these solids of revolution. So a solid of revolution is a solid that is generated by revolving, take note of that, revolving a plane region about a line, which we call axis of revolution, that lies in the same plane as the region. For example, if we consider this here, it's a rectangle. If we revolve this about that one, all the points here will revolve about this particular center here. And once it revolved, we will be able to construct this circular cylinder. And it's actually a right cylinder. Similarly, if you look at this triangle here, this is your region. If you revolve it, of course, you got the point here. It won't revolve. But all the rest, all the other points, will generate the solid. And here you will see a circular cone. If we have this semicircle, all the points here after revolving will be able to create this sphere. Now, suppose we consider this rectangle here, but our axis of revolution is not on your rectangle. Once we have revolved this, these points that are on the rectangle will create the solid, and the space here will not create anything. So after revolving this, we will be able to create a tube-like solid. So there is a hollow here in the middle. So this is our solid of revolution. It's also a right cylinder, which means that the volume, if it's a right cylinder, the volume will be somewhat integral from a to b of a of x dx. Or if it is in terms of y, then a of y dy. But since this is a special solid, we call the solid of revolution, we actually have a very specific formula for our area function, a of x. So how do we do that? Let f be continuous and non-negative on the interval AB, and let R be the region that is bounded above by y equals f of x, below by the x-axis, and on the sides by the lines x equals a and x equals b. Find the volume V of the solid of revolution that is generated by revolving the region R about the x-axis. So in here, we have the function y equals f of x, and the region is from the graph of the function all the way to x-axis. And we are revolving about the x-axis. Now, in order to get this, to derive the formula, we start by getting a rectangular strip. If we revolve this about the x-axis, of course, this rectangular strip will create this particular slab. So in here, this slab is this one here. It's actually a circular slab. We call this slab here or this slab here, disk. This slab will have a radius since you are revolving it about the x-axis. This particular point here remains the center of your circular slab. So this will be equal to f of x. That's the radius. In our case, our function f is above the x-axis. But we have to make sure that we are consistent with our formula. Since it is above the x-axis, we just write the radius as f of x. If your region is below the x-axis, for instance, let us have this one. This is our x-axis, and you have this as y equals f of x. So the radius here, after revolving this, the slab will have a radius negative f of x because the function here has negative values. So the radius will be negative f of x. Take note that radius should be a positive number. In this case, we don't have a problem because our function here is positive. And besides, our consideration is that our function f is non-negative. Now, this is a right circular disk. Okay, this is a right circular disk. So, observe that the cross-section perpendicular to the x-axis at the point x is a circular disk of radius f of x. The area of this region is pi times the radius squared. Correct? The area of a circle is pi r squared. But the radius now is f of x. So, we will have a of x equals pi f of x squared. Which means from our formula, volume equals integral from a to b of a of x dx, we will now have this a of x to be pi times f of x squared. Okay? So this is a very specific formula. Let us consider an example. Derive the formula of the volume of sphere of radius r. So what we're gonna do is to consider a semicircle. So we have this, the x-axis, the y-axis in here, and we consider the semicircle. So pretend that this is a semicircle of radius r. So this one here has radius r. The equation of this semicircle will be y equals square root of r squared minus x squared. If we revolve this about the x-axis, this will generate the sphere. And the slab, well, it's a right circular disc. Okay? So, after revolving this about the x-axis, we will be able to create the sphere. This one Negative r, this is positive r. This slab will run from negative r to positive r, which means that the volume will be equal to the integral from negative r to positive r of pi times the function squared. Square root of r squared minus x squared squared dx. Or simply, this will be pi integral from negative r to positive r of r squared minus x squared dx. Integrating, we will have r squared x minus x cubed over 3 evaluated from negative r to r. This will be equal to pi times, when x equals r, you will have r squared times r. So that becomes r cubed minus r cubed over 3, then minus. When x equals negative r, this will be negative r. So you will have negative r cubed minus, when you cube a negative r, it becomes negative r cubed. Negative r cubed over 3. So if we add this, we simplify, we will have r cubed minus minus there, so that becomes 2r cubed. You got here minus r cubed over 3, minus minus, that becomes plus, but still you have a minus here. So you will have minus 2r cubed over 3. 2r cubed, that's equal to 6r cubed over 3. And 6 minus 2, that's equal to 4. So this will be pi 4r cubed over 3. Or the usual way, 4 pi or 4 thirds pi r cubed. 4 thirds pi r cubed, which is the formula of the volume of a sphere. Okay. Now, let us consider another solid here. Find the volume of the solid that is obtained when the region under the curve y equals square root of x over the interval 1, 4 is revolved about the x-axis. So, here, let us construct the graph. Y equals square root of x. So, y equals square root of x is something like this. Say this is 1, this is 4. The region we are considering is this part here. And we want to revolve this region about the x-axis. So the axis of revolution will be at this point. Now, you don't have to draw the exact solid. As you have seen in my previous solution, I didn't have to draw the sphere. What's important is to know what the radius is. And you will be able to identify the radius by considering your strip. Now, a hint. If your axis of revolution, if your axis of revolution is horizontal, in this method, your strip must be vertical. The axis of revolution is horizontal. The strip is vertical. So in this method, as a hint, if you are given the axis of revolution, the strip that you must consider must be perpendicular to that axis of revolution. And I'm not sure if I have named this method or I've given this method, but we call this the method. I'll write it on the other page. We call this method the method of disk. So in here, method of disk. Well, because the slabs that we are creating are actually disks, the method of disk. So anyway, we have this. The equation here is y equals square root of x. So if we revolve this one, we will be able to create the slab that looks something like this, which is again a disk. So the area function will be pi square root of x squared, which is simply, well, pi x. Therefore, the volume of the solid of revolution will be the integral from 1 up to 4 of a of x dx, in our case, pi x dx. So this will be pi x squared over 2, evaluated from 1 up to 4. When x is equal to 4, we got 4 squared, that's 16, over 2, you have 8 pi. Minus, when x is equal to 1, we have pi over 2. So this will be equal to 15 pi over 2. I mean the volume of the solid that is generated. Okay? So this is the first method. Well, it's because of how our region is constructed. Area under the curve. That's, the region under the curve. You got your function, and then you consider the region between the graph of the function and the x-axis. Now, what we're going to do is to consider the region between two curves. Not all solids of revolution are actually solid inside. Sometimes they have holes or hollows, just like the tube that we have seen earlier. In here, we have this hollow here. Now, what we're going to do is to consider the function f and g, continuous and non-negative, and such that your f of x is greater than or equal to g of x. So we have this. Then we have the region between those two graphs here. But the axis of revolution, if you look at this, the axis of revolution, in this consideration, the axis of revolution is x-axis. The axis of revolution only says that it's not part of your region. It is outside the region. So of course, if you consider this strip here, if you revolve this, only the points inside this strip will create a solid, which means we will have something like this. And then for this one, this part here will create a hole, just like what you are seeing in here. Okay? So how will this change our formula? What is our area function? Observe that the cross-section of the solid taken perpendicular to the x-axis at the point x is a washer. A washer is like a disc with a hole in the middle. This with a hole in the middle. Its area is given by this one, pi f of x squared minus pi g of x squared, or simply pi times f of x squared minus g of x squared. So how did we calculate that? Your f of x is from this point going to your x-axis. Your g of x is from, of course, this point going to this axis here. So in order to find the area of that region is you get the area of the whole thing, including that hole, and then subtract the area of the hole. That's why we have this minus this. Now, normally, we don't know which is actually the f of x or g of x. So what I usually do, if we have our washer, what we need to identify is the bigger radius and, of course, the smaller radius. Smaller radius. And you will be able to identify that once you have your region and the axis of revolution. Take note that the radius is from your function going to the axis of revolution. There will be times when your axis of revolution is not actually your x-axis or not actually your y-axis. So it is better to know or to name this radii as the bigger radius and the smaller radius. So now, as an additional hint, it is possible that the axis of revolution of a solid of revolution is not the x-axis. However, the cross sections are still circular disks or washer. In these cases, make sure to use the proper radius or radii in the area function a of x. So for the method of this, if your your axis of revolution is actually is an edge of your region, then you will use method of this, and the area will be pi times the radius squared. On the other hand, if the axis of revolution is outside the region, then you will be using what we call the method of washer because you got washer. And a of x will be pi times the bigger radius squared minus the smaller radius squared. If you cannot identify, if you mistakenly identify what the bigger radius and the smaller radius are, then you might get a negative value, which is not correct. Volumes are positive. Area is positive. Okay? Let us consider this. Find the volume of the solid generated when the region between the graphs of the equation f of x equals 1/2 plus x squared and g of x equals x over the interval 0, 2 is revolved about the x-axis. I suggest that you always draw the scenario. You always draw the graphs of your function. G of x equals x, it's just this straight line here, 45 degrees. So this one is y equals x, or this is your g of x. Your f of x, it's a square function but shifted 1/2 units So in here, if this is 1/2, your f of x will be something like this. Not to scale, okay? Not to scale. So this one here is y equals 1/2 plus x squared, which is equal to your f of x. And we are considering the interval 0, comma 2. So say this is 0 and say this is 2. Again, not to scale. What's important is we know these boundaries. So we have this and then somewhere up here. Okay? So the region that we are considering is this one here. So now we want to find the volume of the solid of revolution if this region is revolved above the x-axis. Again, it is not necessary to know the exact solid, exact, picture of the solid. What's important is you know which strip to use. So in here, we have the axis of revolution to be the x-axis. The strip must be perpendicular. Okay? So notice that all throughout, if this strip moved from the leftmost to the rightmost, the outer region or the bigger region is always represented by this. Sorry, the outer radius or the bigger radius is always represented by this function. Why? Because, well, if we revolve this, you will have this washer here. And then you will have this hole somewhere here. So notice that the bigger radius is always represented by this function. And the smaller radius is represented by this line here. So let me just write bigger radius, that's equal to 1/2 plus x squared. Smaller radius is equal to x. So the volume, I will just set it up, practice integrating this. The volume will be the integral from leftmost point, which is 0, up to 2. So integral from 0 to 2 of pi times bigger radius squared, 1/2 plus x squared minus smaller radius squared. And then we have the dx. Okay? So practice integrating this. But if I only ask for the setup, then you can just leave the final answer in this way. Of course, if your function, if it's x in terms of y, then you have to do you have to use y as a variable of integration. If x is in terms of y, the strips that you will be using will be horizontal. Your axis of revolution must be vertical. Okay? So you will know which strip to use once you know the orientation of the axis of revolution. If the axis of revolution is horizontal, your strips must be vertical. If the axis of revolution is vertical, your strips must be horizontal. For this method of this, method of washers. Let us consider another example here. Find the volume of the solid generated when the region under the curve y equals x squared over the x-axis over the interval 0, 2 is rotated about first y equals -1. Second, we have y equals 5. Let's do A first. So we have the function or the curve y equals x squared. So let us draw this one, y equals x squared, over the interval 0, 2. So this is 0. Let us just fix this. Say this is your 2, 0, 2. So this is our region. Now, the axis of revolution is y equals -1. Look at this. This is our axis of revolution, y equals -1. Let us set up the definite integral. Axis of revolution is horizontal. The strips that we are going to consider are vertical. Once this strip is revolved about that axis of revolution, notice what will be created. It's a washer. So even if you are considering region under the curve over the x-axis, if your axis of revolution is not the x-axis, then you will still create a hole for your washer. So now, from here, you have to identify correctly what the bigger radius is and what the smaller radius is. The bigger radius is from the center going to the farther function. Okay? The center going to the farther function. So what is that bigger radius? Capital R will be this point is given by your x squared, but that x squared is from this up to your x-axis only. But from this point going to this point, this is actually 1 unit. Well, that's because y equals -1. So the bigger radius will be x minus x squared minus -1, which is equal to x squared plus 1. The smaller radius, well, it is your x-axis going to the axis of revolution. And again, that's just 1 unit. So the smaller radius is simply 1, which means the volume will be the integral from 0 to 2 pi times the bigger radius squared, x squared plus 1 squared, minus the smaller radius squared, so 1 squared dx. Okay? So again, the crucial part here is the identification of the radii. If you're wrong with that identification, then your definite integral will be wrong. Your setup will be wrong. Okay? Let us do letter B. So we still have the same graph. Y equals x squared. Y equals x squared from 0 to 2. Say this is our 2. This point here, this is 2 comma x squared, which is equal to 4. This is our region. This time, we are revolving about the y-axis. Not by the axis. We are revolving about y equals 5. So it's way above in here. If this is 4, this is 5. So the axis of revolution will be at this line, y equals 5. We revolve, we get a strip. Take note, the strip, the axis of revolution is horizontal, the strip will be vertical. If we revolve about this line here, the washer will be something like this. So it's way above up here. Okay. And of course, there's the hole. The hole is somewhere from here up to here. So I hope you can see the solid part. So I'll just I'll just shade the solid part. So this part here, that's part of the solid. And the washer and the hole, I mean, is the one out in the middle. Okay? But now, what is the bigger radius? The bigger radius will be from your axis of revolution, which is 5, going to this part here, which is 0. So all throughout, the bigger radius is 5 units. So the bigger radius is 5. But what about the smaller radius? Smaller radius is, well, again, from the axis of revolution to that part of your function here. If from the axis of revolution going to x-axis is 5, from your function going to x-axis is the function, then the smaller radius will be 5 minus the function. Okay? Which means, again, I'm just going to set this up. The volume will be the integral from 0 to 2 pi times bigger radius squared, 5 squared, minus smaller radius squared, 5 minus x squared dx. So again, just the setup. So again, it is crucial to know the crucial to know what the bigger radius and the smaller radius are. Of course, again, this is not to scale. Of course, you won't see this as it doesn't look like at the center, but the radius is from the axis of revolution going to that part there. Doesn't look like the center. It is not the center, you know. The hole here, as you can see, this one here is not at the center. Then again, you have to know the axis of revolution is always the center. Okay? Now, well, you have the y as the variable of integration case. The solid revolution is obtained by revolving a plane region about a vertical line. One can deduce the following formula. The axis of revolution is vertical. The strips must be horizontal. So, Method of disk and method of washers. You will be given the axis of revolution. The strip must be perpendicular. Once you know the orientation of your strip, you will know which variable to use. Horizontal strips, variable y. Vertical strips, variable x. So this one, the corresponding method of this one, the corresponding method of washer. Let us see. Find the volume of the solid generated when the region enclosed by y equals square root of x, y equals 2, and x equals 0 is revolved about the y-axis. Try to sketch the region. So we have here y equals square root of x is something like this. Y equals 2 is something like this. So this is y equals 2. And of course, x equals 0, it's your y-axis here. So the region is this part here. Of course, this point here, that's equal to 4. Now, the axis of revolution is y-axis. So our strip must be horizontal. Furthermore, we have to write x in terms of y. So from here, you will have x equals y squared. All throughout, if you move this strip along the y-axis from 0 up to 2, all throughout, the radius is this function. After revolving, you will create the disk that looks something like this one. So you will be able to create a disk that looks something like this one. So it's a disk. So anyway, the volume will be equal to the integral from 0 to 2. Take note in terms of y, lowest point is 0, highest point is 2. The radius of the disk is from this one up to your function, but the equation of the function is this, x equals y squared. So you will have pi times y squared squared dy. Okay? For the last set of examples here, find the volume of the solid generated when the region between the curve y equals x squared and the x-axis over the interval 0, 2 is rotated about the y-axis, the line x equals -1, and the line x equals 3. So in here, we have y equals x squared, y equals x squared. The x-axis over the interval 0, 2, 0, 2. So the region will be this here. Let me draw the three scenarios. Let's copy this one here. Copy, paste. So this is the second one. Let me put it here, the second one, and then the third one here. For the first scenario, letter A, y-axis. So y-axis is this axis here. So the axis of revolution will be this one here. Notice, since the axis of revolution is vertical, the strips must be horizontal. After revolving, you will be able to create a washer. Okay. Next one, letter B, x equals -1. X equals -1 is somewhere here. So you will have this equation, x equals -1. Again, vertical axis of revolution, the strip will still be horizontal. And of course, if you look at this, since in letter A, the axis of revolution is the y-axis, the radius is from this point going to this point. That's the outer radius. Let me write the outer radius here. The outer radius will be from 2 to this one here. The inner radius, or the smaller radius, will be from your axis going to this function. Since we are considering horizontal strips, we have to write y equals x squared as x equals square root of y. So the smaller radius will be square root of y. But what about letter B in here? Of course, x equals 2 is from this point up to this point. But this is the axis of revolution. So we have to add this portion. This portion is 1 unit, which means the outer or the bigger radius will be 2 plus, let me write it as 2 minus -1, which is equal to 2 plus 1. The smaller radius is from this point going to this point. Here, the equation is x equals square root of y. Square root of y is from this point up to this point only. So we have to add this 1 unit, which means the smaller radius will be square root of y minus -1, which is equal to square root of y plus 1. Okay. Lastly, for letter C, the axis of revolution is x equals 3. So this is your x equals 3. This is the axis of revolution. Vertical axis, horizontal strip. So when we revolve this, you will have this, and then we have this, and then of course there's the hole here. But what is the bigger radius? The bigger radius is from this point going to this function. So this point going to this function. The bigger radius will be r equals. This is 3, but 3 is from this point going to the y-axis. So that's equal to 3. This point here, part of the function, is from the function going to this one. But we only want from this point going to this point. And our tree is from this point to this point. So we have to subtract this portion. But that's your square root of y. So 3 minus square root of y. And then the smaller radius is from this point going to this point. Same, you will have your 3 minus 2. That's your 1 unit from this up to this one. So now we have this smaller radius and big radius for each. So try to set up the definite integrals and practice if you want to. I mean solving them. Let me just write the setup for this one, for the third one. So in here, take note that x, we have up to x equals 2. So the highest point here will be equal to 4, correct? So the strip will run from your y equals 0 up to y equals 4. So the integral from 0 to 4 of pi times bigger radius squared, 3 minus square root of y squared, minus 3 minus 2 squared dy. So this will be the setup for this solid. Take note that these three here, they will generate different solids. Okay? So that will be the end for this topic. Volumes using the method of this, and washers. For our next video, we'll be discussing another method of finding volumes. We call that method of cylindrical shells. So that's all from me for this video. I'll see you in the next one.